Hello and welcome to this video. So all of the other videos that we've done in this course so far have been John and I going through some theory or some content, and this is going to be the first video where we're actually doing something practical. So get excited. So in this video we're going to be taking apart and disassembling this PV inverter just here. And I'm here with Leonardo, which I'll introduce in a second, and we're going to be looking at all the different components inside of this PV inverter, and we're going to be trying to bridge the gap between the content, which we've learnt in this course so far, and how this is practically implemented in a device like this, which is available on the market. So Leonardo, perhaps you could introduce yourself.
Hello everyone, I'm Dr. Leonardo Callegaro. And with Matthew today, I'm going to show you what's inside this commercial PV inverter.
Fantastic. All right, well, do we want to get started with the top panel just up here? Perhaps you could run us through each of the important components just here.
So this is the top panel where we connect the electricity and the input from the solar arrays. And we can see on this side we have two DC inputs. We can recognize the DC from the color of the cables, one red and one blue. Mm-hmm. We have an output here on the other side, which is the AC single phase output. And then we have some communication ports that you can see on this side here, the RS232 to program the inverter, and another communication port, which is called DRM. And it's a demand response management port, and that one is for the grid operator to decide whether the inverter needs to be remaining turned on or turned off in case there are some problems in the grid.
Fantastic. So I had a couple of questions, Leonardo. So we said we had two DC inputs. Why would we bother designing an inverter to have effectively two DC inputs?
Yeah, that's a good question. I also thought that the first time I saw an inverter. That's because you can connect solar panels, for instance, from a different side of your roof. You can put an array on one side of the rooftop and an array on the other side. So these two arrays may have a different power coming in because of the orientation. And so it's good to have two DC inputs so we can separate which input goes to which array.
Fantastic. I think that was pretty much all that we had. So we've got also an earthing connection here, which is quite important. So we generally connect that to the earth at home, I guess.
Yeah, of course, for the safety of ourselves at home, we need to make sure that all the earthing connections are done properly. And that's why we have the earth stud here in front. So probably one of the most important parts of the front panel.
Fantastic. All right, well, perhaps do we want to take the lid off it? And,
yeah, sure.
Yeah.
Let's turn it around. Shall we?
Shall we do it? So we'll take the screws out, which we've already unfastened.
Yeah.
So before we kind of take the lid off, perhaps we could go through the just this interface that we have here. So what would we kind of expect to see on that interface there when it's on?
Yeah, that's a good point. So in this interface, we can see usually the value of the AC voltage, the current that the inverter is putting into the grid. And we also see the value of the DC side, so what's coming from the solar array, so the DC input voltage and current.
Fantastic.
And obviously, if there is some alarm or for some reason the inverter stops working as it should be, the alarm code is also usually displayed there.
Oh, okay, for troubleshooting purposes.
Troubleshooting, exactly.
Yeah. Cool, fantastic. Oh, let's perhaps we can remove the lid off. This is exciting.
Cool. Oh, we also forgot to say this is a 5 kilowatt inverter. So just to give an idea about the size of the inverter. So yeah, it's quite a big size, and we can see that the cooling is not done through any fans, but it's all natural cooling, and it occurs via heatsink, which is installed at the back of the inverter.
Is that common for inverters, like to not have a fan?
Yeah, it's quite common, especially for rooftop solar installation or inverters that you install at home. because usually the fan is a point of failure for the reliability. It doesn't last for many years, so it's quite better if they don't have it. But yeah, the weight is the point.
Yeah, true. Okay, all right. Well, perhaps we could go through. I mean, the first thing that I kind of see over here, we've got a control board here, and we've got some components over here. So do we want to kind of go through each of these components so we can see?
Yeah, perhaps we should show what we were seeing before. So here is where the display is, and this is the control part of the inverter.
Yep.
And we have two boards, and then after the control board we have all the power processing stage. Perhaps we should remove the control boards first and then talk through the power stage.
Absolutely. Yep, the power stage is probably what we're interested in this subject. So yeah. So the control board's kind of more just towards the control with respect to the display of this interface. That's what that board would primarily function.
Yeah. So let's do it.
So just two screws off.
So this is the first display board, and under this board we can see that there is another control card, and in this control card we can see that there is a micro controller here, this big square chip, and that is a Texas Instruments fixed point microcontroller. So in commercial equipment the control tends to be implemented in fixed point type of microcontroller because they are more economical.
Yeah.
And what sort of algorithms will be implemented in that microchip?
Well, I think like if we date it back to our the stuff we've learnt in the course, I'd imagine they'd have a maximum power point tracking algorithm in there. They'd also have, I'd say, some form of fault detection. So as the frequency gets too high, they'd have to implement some algorithm there if it's not within the frequency bounds to have a cutout mechanism, and also with the voltage as well. So basically it'd be all to do with the grid synchronization process, which we've actually covered in the course. So if you don't understand what I'm saying, please do go back through the grid synchronization lectures, which is I think week 5, where we cover the control of basic H-bridge inverters and how we synchronize these to the grid. So I'd imagine all of those things that we cover there would probably be, the algorithms would be stored in that processor.
Yeah, sounds right. Probably that small component is the brain of the inverter, which is doing all the measuring, the processing, and the control functions.
Current control, power control stuff. Yeah.
Exactly. So all the things that you learned in the course are actually implemented in this little component here.
Fantastic.
So should we go and remove the control board?
Absolutely.
Okay, another component to be removed. There's a lot of mechanical supports.
Ah, yeah, so that's there for mechanical support, yeah.
Yeah.
That's something we don't really talk about in this course so much as kind of, you know, the mechanical side of these inverters. Like we talk about the power electronics side of things, but we kind of haven't really covered too much with respect to mechanical or shrouding or even the heat sinking of a lot of these components. So, but be aware that there's a lot of design engineering that goes into building these commercial devices with respect to the physical shrouding of different boards and components, as well as the thermal management of these components as well.
Okay, so we remove the AC connection.
Fantastic.
So we can see these are the AC cables, and we can see that there is some sort of coil looped around the AC cable with probably a ferrite core.
Yep.
And that's probably to get rid of some typical electromagnetic disturbances, which can be conducted through the cables.
Yeah, so that'd be a line inductor. Of some
Yeah,
description.
yeah, or some common mode choke.
Okay, yeah.
On this side, we can see where the DC cables are connected. So we can fairly say that this is the DC to DC stage of the inverter, whereas this one is the DC to AC part of the inverter.
And we could see that there's actually two boost converters. And I was going to throw that to you guys, the viewers, to kind of answer below in the Open Learning website why you would think we would have two separate boost converters here and not just one. So yeah, if you could post below the answer to the question and we can start a discussion on that, would be great.
And also, why boost converter and why not a buck converter?
Why do we need a boost converter in the first place? Fantastic. Yeah, definitely answer that question too.
Yeah, that's a very valid question. Okay, so we have seen the DC to DC boost and the DC to AC. We can see also these components at the back here. They are the inductors. So we see we have two inductors because we have two boost converters. And on this other side are the inductors of the LCL filter of the inverter. So a good question which we can address by following the course is, why do we need an LCL filter at the output of the inverter?
Fantastic. John should have answered that one in the grid synchronization lecture, but that'd be great if you could also post that below what the answer to that question is. And so go and review the grid synchronization screencast, I think it is, for the answer to that. And yeah, it'd be great if we could get a bit of a discussion on that as well.
Yeah, sounds great. So perhaps we can remove now these wires and see where are the main power electronic components, which are the IGBT
That'd be great.
and the diodes.
Yeah, the stuff we're interested in, the power electronics.
That's right. So let's remove this. This one. Okay. Yeah, this is ready to come off. Yeah, thank you. Yep.
So we've just removed the board out of the mechanical shroud here. Perhaps we want to take the board out and talk about kind of what's in the bottom of this.
Yeah, so we removed the main motherboard where the switches and the capacitor, inductor and other components are installed. And we can see that there is this metal plate is the heat sink. And we can see that there are some small rubbery type of material connected between the heat sink and the back of the board. And that's to get rid of the heat that the switches produce during their operation. So as we know, power electronic switches have switching losses. And we somehow need to get rid of the heat, which is get rid of the losses, which are heat. And we do so by transferring the heat to the heat sink, and the heat is better conducted through this rubbery mat.
Fantastic. I imagine there'd probably be some thermal paste under it as well.
Yeah, that's right. In fact, we can see that it's not very easy to remove. They are glued by some sort of paste to the heat sink.
So for people who aren't aware, we generally use some kind of thermal paste when we're connecting or putting an IGBT onto a heatsink, and that helps the heat conduct from the surface area of the switch to the metal itself. Because obviously we want to channel as much heat away from the semiconductor junction as we can, and if we can make that transition more efficient, it means that the heatsink will work better. So generally use some kind of thermal conductivity paste.
Sounds right. So we now talk more about the board with the main power electronic components.
Don't need that anymore, so we'll get rid of that.
Sorry. Okay, so this is the main motherboard, where on this side we have the DC to DC stage, and on this other side we have the DC to AC stage. We have some DC link capacitors. The inductor is mechanically mounted with enclosure, so we cannot see it anymore. But we have some EMI filters, like this one for the DC input, and this coil looks like a common mode type of filter. And this is probably a Rogowski coil to measure the AC current at the output of the inverter. What else can you spot which is worthy of notice?
Well, I was going to bring back the attention to this common mode filter. So we talk about in one of the screencasts the fact that if we use just a traditional kind of H-bridge inverter, we end up getting some common mode current issues. And the idea of there being a transformerless inverter, so one that we don't have a transformer, we start to get these common mode voltage or common mode current pathways. And one of the methods for dealing with that is to obviously put in a choke like this. And the common mode choke effectively won't allow these common mode currents to pass.
Yeah, that's...
And that's... So correct me, but this looks like a transformerless inverter, because I can't see the transformer anywhere, and that's kind of one method of doing that. So yeah, I see that. I can also, I know on the other side we've got the IGBTs, but we've got, aside from the capacitors here, what's this component over here? Do we know what that is? That looks like yet again another coil of some description.
This coil here? Yeah, this is probably a Rogowski type of coil to measure the AC current that is injected into the grid from the inverter. So don't forget that the AC current injected must be in phase with the grid voltage.
So that's the primary kind of like method of measuring.
Measurement, yes.
Yeah, okay, is that coil there? Fantastic. Have we got any other measurement devices on here?
Yeah, probably we can see these boxes here. They measuring the current or the voltage, or they might have some sort of isolation as well. So you sort of decouple the noise from the power stage to the measuring and control stage. Other components, we can see these white chips here. And they are very close to the terminals of the switches. And so these are the gate drivers. So they are also very important components, and they are the components where the controller sends the signal, and after the gate driver, the switch turns on and off, right?
Fantastic. I mean, that's probably a good thing to kind of talk about. So we haven't really touched the practical side of actually designing a board with some form of power electronics in it. And when we're driving an IGBT or indeed a MOSFET, we generally use a component like this, which is a gate drive IC chip. So what are some of the purposes, I guess, of a gate drive? Like why wouldn't I just directly connect from the controller a signal to the gate of the IGBT?
Yeah, that's a good point, because the controller gives us an output voltage, can give us a PWM waveform. But the power this signal is carrying is not enough to drive a switch. So that's why we need a gate driver. The gate driver, we have a control input at a very low power, but then it will have its own power supply, and at the output it will have a much higher power level that is suitable to turn the switch on and off. Absolutely.
A lot of gate drive ICs nowadays too perform some basic protection too of the gate drive terminals for the switch. And that's all, like, if you're interested in this, definitely go and research a gate drive IC. You can find them and find the spec sheet and have a read kind of on how they're installed or implemented on a board like this, and some of the forms of protection, because this gate drive chip generally comes with, inside of the spec sheet, a different circuit that's required, and a lot of the components you put on there would govern the switch on times and delay times and latch times for the switches. So yeah, have a read of the spec sheet for more information external to this course.
Yeah, I agree with that. The gate driver is one of the most important components in a power electronic converter. but we give most of our time to talk about the MOSFETs and the IGBT, so the gate driver also is very important.
Absolutely.
And yeah, on this side of the board we can see some isolation transformers, and they are powering the gate drivers. So it's good if the power of the gate driver is galvanically isolated from the rest of the board, so to not to conduce disturbances into the gate driver and then to create noise in the IGBT or in the driving stage of the IGBT.
Absolutely. It's also important to note the reference for these gate drive circuits will be different for the lower switches as compared to the upper switches. So that's very important. Obviously the reference for the gate drive signals for the lower switches can be just the negative rail, but we can't do that for the middle switches, because otherwise we'll end up shorting out. So we actually have a different reference for those gate drive circuits for the upper switches, and each of them will need its own separate supply. Is that correct?
Yeah, that's correct, because to drive a switch, if you think about a MOSFET, you need to supply a voltage between the gate and the source, but the higher switches have the source which is not connected to the ground, and that becomes a problem when it's time to turn the switch on and off, because the power to the driving stage of the high side switch needs to be provided from an isolated source, or there is a lot of information on this topic, and gate drivers.
Fantastic. Well, perhaps we could move on from the gate drives.
Sure. Yes, we can see on this side a small heat sink, another small, probably a small coil, and what looks like a small power converters to supply all the voltages that we need for the control stage of the inverter. For instance, the supply of the gate driver might be 15 volt, but the DC from the solar give us 100 volt. So inside the inverter we need a small housekeeping, it's called power supply, to have all these smaller voltages accessible.
And that all have some isolation associated with it as well, as you
Yeah,
said before.
it sounds right. It's always isolation is always a good thing, but it's also expensive. That's why.
Yeah, and having all these coils. Was there any other exciting component on this board?
Perhaps we can look at the switches.
Yeah, I think that'd be great if we flip the board over and we can actually physically see what an IGBT actually looks like. So yeah, let's go ahead and flip the board.
Let's do it.
Ah, fantastic. So these here are our IGBTs. Yeah.
Sure.
So yeah, that's kind of, if you haven't seen one of these before, that's exactly what they look like. And we actually go through in week 10 the different package types that you can get for an IGBT. So we look at this package type here, and it looks like a plastic package type to me. But we also go through the puck package type, which isn't used in this inverter in week 10. So refer to that for more information. So what do you take from looking at the switches here, Leonardo?
Yeah, we can see the IGBTs, which have three pins, and we can also see some diodes, which have 2 pins. So on this side, we remember the DC cables were entering, and we see one IGBT and one diode coupled by another IGBT and another diode. And these are in fact the switch and diode which are connected to each boost inverter. Okay. So boost converter, sorry. And so we have 2 boost converters with one IGBT and one diode. That's the first boost, and then the other boost is here. On the DC to AC conversion stage, we have a lot more components, but we can see we have 1, 2, 3, 4, 5, and 6 switches, and 1 and 2 diodes. So I think that we probably have an H bridge with at least 4 switches, and then there are some additional switches and diodes to get rid of the common mode voltage, because the inverter is transformerless, or the topology obviously is proprietary, but from what we know, it's commercial. We know that it's not only a simple H-bridge, but also some extra diode switches are used. For instance, the H6 topology or the Herrick topology.
Yeah, fantastic. And we cover those in the screencast as well, so review those to have a look at the circuit diagram and how it works. Fantastic.
So another element that we can observe is this sort of soldering here, which is made on the PCB, these lines, and they are probably to help the system to get rid of the heat, which is inside of the PCB.
Okay, so you'd often add solar onto these tracks to just give them a little bit more conductor.
That's correct.
So, yeah, I've done that one before, so.
Yeah, some tricks that we cannot explain during the lectures, but.
Yeah, when you're designing a board, absolutely. You've always got to think about the width of your tracks and how much current that can actually take, and often adding some solder, to the tracks can help just carry that little bit more current that you need.
Yeah.
Fantastic. So was there anything else that we wanted to cover concerning the IGBTs and diodes at the back of this board? Or?
Yeah, I think the most important part was to show the two boost converters with a simple switch and a diode for each converter. But then also to notice that there's not a simple H-bridge on the DC to AC stage with only 4 switches, but there's a lot more to it. And especially because of the common mode voltage issues and the transformerless inverter. So what we really study in the lecture is really applied in the practice, and we can see it here with our eyes.
Fantastic. Oh, well, this is I hope everyone's enjoyed the video. I definitely have, taking part in a commercial inverter like this. I'd like to thank you for coming on,
Thank you,
Leonardo.
Matthew.
Yeah, thanks very much. Like taking some time out of your day. I think it'd be great to possibly give us maybe a quick 2-minute summary of what you're working on at the moment in the PV inverter domain. Yeah, for someone who's kind of interested in power electronics and inverters, giving a bit of, like, to the students perhaps a bit of like an application that power electronics is really important at the moment and a problem that we're trying to solve.
Yeah, so as you know, power electronics, it is really important, but is probably less known than the solar panels and the renewable sources. But what controls the power coming from the solar panels is an actual inverter. And there is a lot of this power installed in Australia. There is so much of it that it's like having many power plants installed all around the countries. But the only way to determine the behavior of each inverter, if there is a grid disturbance, for instance, if the grid voltage goes too low or the frequency goes off 50 Hertz, is to make sure that the inverter complies with the Australian standard. With the Australian standard. So in my current work, we make sure that these inverters comply with the Australian standard, which is the 4777 version 2015. We apply some grid disturbances like voltage sag, frequency variation, rate of change of frequency, and we make sure that the inverter remains connected, keep delivering power to the AC grid, and basically complies with the behavior which is imposed by the standard. Because if these inverters don't comply with the standard, they might disconnect from the grid altogether, taking away a huge chunk of power generation all of a sudden, and create a lot of problem for the grid operator, which has to schedule the amount of power which needs to be generated and put into the grid, and needs to maintain a balance between the load and the supply in order to keep the frequency constant and to make sure that our house appliances are working properly with receiving the rated voltage and possibly the rated frequency.
Absolutely. So I think, like, to sum up, pretty much there's standards on the power that these inverters must deliver to the grid. So they must have a certain frequency and a certain voltage in particular, and if they sway away too much from this, then the inverter can disconnect. But there's also standards on the inverter keeping connected to a grid, or what's called riding through a fault. So what we don't want happening is a fault way down the grid over there that's not related to us at all, tripping out our inverter, or perhaps tripping out a big chunk of inverters and taking out a lot of power to the grid, as Leonardo has just said. So it's a pretty big issue at the moment. Inverter riding through faults. Becomes really difficult to do fault protection on these inverters, as John mentioned in one of the screencasts, because traditionally the fault current you get from an inverter like this is quite low in comparison to other devices. So it's a big field. It
is a big field.
There's a lot of work on it. Oh well, I hope you've enjoyed this this video, and yeah, join us for the rest of the course, and I hope you can take some of the application-based, industry-based knowledge into the rest of your engineering career. Thank you very much.
Thank you.